U substitution tends to work when you see both a function and its derivative as part of the same problem. If you look at the problem on the left, what you'll see is that the same integral contains both an x cubed and a 3x squared. This fact alone doesn't guarantee that U substitution is going to work, but it does suggest that it might be useful. So I'll show you how this works, and over time you develop intuition about what types of problems U substitution works with and how to use it. So what I'm going to do is I'm going to define a variable U, and I'm going to let it equal x cubed. Now, why did I choose the x cubed? Basically because it looks like it's the inner part of the function. We'll get to that, but if u equals x cubed, then the derivative of u, du over dx, is equal to 3x squared. Now, if I multiply both sides of that derivative by dx, I get du is equal to 3x squared dx. In general, I'm going to skip the whole step of multiplying by dx, and I'm just going to find the derivative and write a dx after it in the future. But for this first problem, we'll do it that way. So what you want to do now is you want to look for these expressions as part of the original problem. It'd be a little easier to see if I rewrite the original problem. So let's write the integral of, I'm going to rearrange this so it's written as sine x cubed times 3x squared dx. And what you can see here is that this expression x cubed is u. So this larger expression here is sine u. And this expression here is exactly what du is. So what that means is that I can rewrite this integral as, this is going to be the original integral, 3x squared sine x cubed of sine times sine x cubed dx is simply equal to sine u du. This is useful because this is an integral that we know how to find. We know that the antiderivative of sine of u is negative cosine of u. And then finally, we replace the original, since we started with x, usually you want to get back to x. So since u is equal to x cubed, we can replace u with x cubed, and the antiderivative here is cosine of x cubed plus c. And there's the antiderivative of 3x squared times sine x cubed dx. Okay, on the right we have a problem that's similar but not quite the same. So I had mentioned that generally you want to choose u to be the inside function. What I mean by that is the thing that looks like it's being wrapped, like something else is wrapping around it. In this case, there's a cube root, and just to be clear, this integral is the integral of x times the cube root of x squared plus 9. So the thing that looks like it's inside, in the sense that it's inside that radical sign, is x squared plus 9. So I'm going to let u equal x squared plus 9. That means that du is equal to 2x dx. Derivative of x squared plus 9 is 2x. So let's go back here. The integral, if I rearrange this a little bit, I want to put the thing that looks like du next to, and I want to put them next to each other. So this, I'm going to rewrite it as x squared plus 9 times x dx. We can readily see that this is the, sorry, I forgot, this is cube root. We can readily see that this is the cube root of u. This doesn't quite look like du, but it's very similar. If I take the original expression for du and divide both sides of that equation by 2, I get 1/2 du is equal to x dx. So now I can see here the exact expression that appears in the integral. So this part is going to be 1/2 du. Therefore, I can rewrite the original integral. So this is going to be the cube root of u times 1/2 du. This is going to be a little easier to work with if I put the 1/2 out here and rewrite cube root of u as u to the 1/3. So that's going to give me 1/2 times, to get the antiderivative of u to the 1/3, I add a full 1 to that fraction. So that's u to the 4/3 over 4/3. And that gives me 1/2 times the reciprocal of 4/3 is 3/4. And I get u to the 4/3. So this gives me 3/8 u to the 4/3. But I want to convert it back to u, so this is going to be 3/8 x squared plus 9 to the 4/3 plus c.